Thank you. Um, this is not so complicated as the things Wiegand does. We just need some circles and some lines. Yeah. And we want to do graph algorithms in mathematics for computer science. And I will just tell you some words what we do in our lectures. Then I want to discuss about something about graph drawing and how to randomize things. And then I will present our solution, what we did. And then, of course, I show you some questions. Um, um, what we are doing, we do just some foundations of graph theory, and then we do some algorithms, and we do um, first depth first search, breadth first search, cross-gulls, and Dijkstra's algorithm, and they are all algorithms that build a spanning tree. So they have a lot of things in common. And if you see such an algorithm as a student, then you say, well, a lot of formulas. Let's see the graph and what we are doing with the graph, and not such an algorithm because no, it's hard to understand because they are in the first semester and then they are not used to it. And of course, when I present this algorithm, then I'll do the things at the blackboard with chalk and maybe with more than one color. And this is maybe such an exercise. We have a weighted graph and we want to have a minimal spanning tree. And this you can do just by pen and paper. You can just mark the edges with color, and then that we want to see in which order the students number add the edges to the tree. And so what we want to have afterwards is something like this. So we just, if you know Kruskal's algorithm, you just see here you have to start with the edge with the lowest weight. This is here -1. And then you will have here a 1 and here a 1. It doesn't matter in which order you add them to the tree, and so on. And afterwards, you get such a spanning tree, and you can say what minimal weight the tree has. So this is a normal pen and paper work. And then we came up with the idea, well, we want to train the students maybe on the computer, maybe with Stack, maybe with something else. And they want to train it. And so maybe they want to have more than one of these exercises. And what can we randomize? Of course, you can randomize the number of the vertices, the number of the edges. You can randomize the edge weights, the structure of the graph, the positions of the vertices. And well, you have to think what does make sense. And I had student thesis last year, I guess. It was not a JSXGraph, and the student tried to randomize the positions of the vertices and came up with graphs like this. And if you think, how will I add the edges to a spanning tree? Then you have to click here on the edges, and then it's not really good to have crossings of edges. Yeah, so randomizing the positions of the edges is maybe not a good idea. And as you can see, he always has the same number of vertices. He only randomized the positions of the vertices. Then he also did Dijkstra's algorithm, and here he only randomized the weights. And I think he also had, so here you have this always the same starting point. And he said, well, just here we have some extra um, um, nodes where we want to go. So this is the E here and the F there, and we want to have the shortest path. This is how they did it in the lecture of algorithms and data structures. And they also had something what is strange to mathematicians. They made the algorithms the way unique. So if there you have more than one possibility, take the way to the vertex with which is first in the alphabet. Yeah. So of course you can make things unique, but maybe this is not what we want when we check things with stack. So I already had some graph algorithm things in Moodle, and the most unflexible solution would be, well, there is a picture of a graph, and you just have to drag and drop the numbers onto the image question, and you see here the convention to visit the far most left. If you stand on a vertex, have a look to the graph and take the most left neighbor. So you in this kind of question, you have to do it this way because you have only one possible solution. Then, okay, we want to have nice graphs. Take the most flexible solution. Take a graph drawing algorithm. Maybe with such a spring-based algorithms, yeah, you have attractive forces between the nodes, and you have electrostatic forces between the nodes, so you have some iteration, and then some when you have equilibrium or near equilibrium, and then you get maybe some nice pictures like this. We did this some years before. This is an algorithm for genetic networks in 3D, and it's easier to do it in 3D than in 2D because of these hub nodes. So maybe this is a little bit too much. And we already had some stack questions for graphs where we had some randomization. So maybe you have some graphs, some pictures of the graph, and you randomize over the pictures, and you randomize over the letters for the vertex names. And then you have, of course, for this kind of questions, already enough randomization. Yeah, but we wanted to do algorithms, and we wanted to have interaction via clicking on edges. So this is what we did. And I have to say the most work was done by a student of mine, Shahab Abtabi, who did this bachelor thesis on this topic. And he also came up with this idea, and it's really a nice idea. We start with a given graph, and you see it's a nice planar graph. The positions of the vertices are fixed. We have no crossing, of course. And if we take out some vertices and some edges, things stay planar, and we get some randomization. So, and when we do so, we get here some variants, and you see the variants are different enough. They are planar by construction, so we have no crossing. If you want to click on something, it's easy to find the right edge, and the teacher can adjust the complexity of the exercise. You can choose minimal and maximal number of vertices, and you can choose the density of the graph. So how many edges do you want to leave from the original graph? And so these parameters are really easy to understand and also to set. And of course, if you say, well, I just want to have 5 vertices and so on, so or I take all 14 or whatever, then you get a really adjustable complexity. And of course, the weights are randomized. So maybe we just have a look at the. Can you see my browser now?
Yes.
Yes. Okay. Prima. So maybe we start with Dijkstra's algorithm, and I prepared here something for you. And Dijkstra's algorithm is you just have a starting point, and then you click on an edge and say, well, I add it to the spanning tree, and then of course we go from here to here, and we have here 2 choices. We take, of course, the thing with a smaller weight here. So okay, we have 3 possibilities. We have to take this one, and then where we can go here, maybe here or here. You can go here. Okay, it's not the best idea. Just go here first, and then you can go here, and then you have the possibility from here to here or from here to here. And the way will be equally long, because if you see here from A, yeah, okay, from here to here we have 8, and then we have 6 plus 3, or we have 1 plus 8. So they are equally long. So just take this one. And we can check. And we did it right. And the only thing what is not so nice is that we cannot keep the student's answer here. So we did it here again. So then you can see your solution, and also the distances are right. This is what I prepared for you. And here we have the solution, what is pre-computed. So this is a model answer. And you can see the model answer is different, but of course the student's answer is also correct. So these are here only 2 possible solutions, but both are of course correct. So jetzt muss ich when you have Kruskal's algorithm, here for this case, we have a lot of more possibilities. So we start with the, for the minimal tree, we start here with the 1, which is the smallest weight, and then the next bigger one is 2. And then we have 4, 4, 4, and 4. So we have a lot of possibilities. So maybe we take just this one, and then this one, and then this one, and then this one. And then we have 2 5s, this one. And now we have a tree. So we have, it is connected, and we skip, of course, every other thing. Of course, this 5 would have been wrong because it closes a circle. So just have a look. This is our solution, and the possible solution is a little bit different. Here Also, the trees are different. We have here the 4 was done here in the 3rd step. We had it here in the 4th step. So this can be seen here also by the students. So when we have a look at the other questions, you will see that it's not so new if we have a bright first search. It's more or less the same idea as with the Dijkstra's algorithm. Yeah, here we have we have to do it in red first. So we have to go here, maybe, sorry, here and here. And this is already done. It's here and here. And then we go here and here and here. So hopefully. Okay. Let's see what I did in another way. Start here. So this is everything is okay. 5, 6, 7, 8, 9. Okay, this is not, that should be not in this way. So maybe it's still a bug. So maybe I have to check what Shahab did here in this. Yeah, this is already enabled from this. Yeah, that's correct. From 6, we have to go here and here. So I was wrong, and the algorithm was right. So and so it's more or less what we wanted to have, like the pen and paper exercises. Just draw your graph with your mouse and see what happens. And here we can really do the same as we did before in class. So that's what I wanted to show you. On the slides, it's only just a backup. So I can, when I upload the slides, you can see what I did here. Yeah, so that's the are the same. And what can we say about it? Of course, graph algorithms are well suited for visualization and for interaction. And yeah, of course, JSXGraph is a good tool for practicing graph algorithms. We have a lot of exercises due to randomization. I cannot say how the students find these exercises because they will be in use this December. So I cannot say anything about it. But we have a bachelor thesis where we try to have an editor for graphs. And so we can have exercises where the students have to create their own graphs with certain properties. So also maybe something for the next conference or somewhere else. So that's what I wanted to tell you.